All right, everyone. Welcome to our next talk coming up here. We have the schadenfreude of unreliable exploits. We've got Mikhail and Tim up here, so please welcome them to the stage with a warm round of applause.
Hey there. I'm Tim Carstens. This is my buddy Mikhail, Mike, if you can't handle that. And we want to talk a little bit about two stories. One of them, the story of Windows error reporting, told at least in part. And two, the story of what a crash dump looks like when someone else is working on making your day real bad and, just kind of rolling dice to do that. I want to talk about this slide for just a second. So this is your typical disclaimer. The project that we are presenting on was funded by Uncle Sam. This was one of the projects under the DARPA Cyber Initiative, the Cinder program, run by our good brother Mudge. And Mudge has a message that he wanted me to share. And the message is this: if you have interesting research that you think is of value to this country, he wants to pay you to do it. And he's already paid me. I don't really owe him at this point. But I will go ahead and say that if you want to talk at all about what it's like to work with DARPA, what it is to work with Brother Mudge, I can tell you all about that. The Cyber Fast Track program is really slick and very easy to get a lot of cash up front to do your hacking. And he is interested in all projects that will help this country improve its cybersecurity, both within the government sector and within the sector that most of us live in. So this project right here would not have been possible without their stuff, and I really want you to think very seriously about taking advantage of the offer that he's put forth in his Black Hat keynote. All right, but now on to my story and Mikhail's story. So here's a tale, and I think that we've seen this, especially if you've done any incident response, which I suppose a lot of folks probably have. Like all good hackers, Bobby starts his work by finding Ode, not by just going out to Millworm. And he goes ahead and he finds some bug, and he cooks up an exploit, and he sends a malicious document to Susie. And Susie tries to open the document, but it crashes. And Susie keeps hitting the print button, because that's what users do, and she keeps opening it, and it keeps crashing until eventually it doesn't crash. And then she sees a picture of a cat. And she doesn't know Bobby, but she's still thankful that she sent him, that she got a cat from him. She's all excited. But by now, Bobby's got root on Susie's laptop. And Susie's not paying attention, but users, Susie, app data, local crash dumps now is full of a bunch of .dmp files that tell the whole story of what Bobby just did. And there you go. And so, Susie's going to go home and and talk to her husband Hank and explain Windows is awful and everything crashes, but I got this great cat in the mail. And that's going to be the symbol of the day for her. So if you're not familiar with the process on Windows, when a program crashes, the default behavior, and this is infinitely configurable, and so this won't happen every time depending on deployment, but the default behavior is that wherefault.exe launches, and it runs as the same user as the crashing application. Wherefault, where is in Windows error reporting. Wherefault does a whole lot of work. If you open it up using any of the sysinternal tools and take a look at the syscalls it makes, it spends about 900 years studying the registry. In particular, these keys here in current user and in local machine regarding Windows error reporting. And it checks for a lot of different stuff, but most pertinent to us, it checks to see if Windows error reporting is enabled or disabled. A lot of corporate environments disable it instead of shipping data to Microsoft. That makes sense. Even if it's enabled, you can configure it to not send crash dumps to Microsoft, but rather to send it to your own server, which is interesting. You can configure whether or not it will even show that dialog to the user. And you can also control, especially if you're suppressing the user interface, you can control how much information it will send. And I'll talk about that in a little bit. When these slides are posted on the Toorcon site, there's the link right there to all the information on the registry keys if you want to experiment with that locally. After it's consulted the registry to obtain configuration information about reporting, it generates what's called a mini dump file. And if you're a developer on Windows, you probably know the mini dump format. It is basically just an archive that contains information about register state, some contents of memory, and I'll talk a lot about that. It talks about open file handles. It talks about what modules are loaded. And there's a whole bunch of auxiliary information as well. For some builds, it sometimes includes debug information, comment strings, and stuff like that. You don't see that much for released applications, hopefully, but they are present. Great. Collecting the crashes is really simple. There's actually two protocols. I'll talk about Windows 7 and Windows Vista and Windows Server 2008 predominantly, but XP and Server 2003 have their own reporting. In those more modern Windows, the process is really straightforward. It's XML over HTTPS, depending on how you want that set up. The protocol is MS-SARE2, SARE's in corporate error reporting. And there's the link to the information about that. It's a published thing. You click through the usual kind of Microsoft look at a spec doc, and then there you go. And the relevant keys for configuring a server are just, what port to connect to, what server, do I use NTLM or not, so the user can authenticate to the crashing collector, and do I work with SSL or not, because that should be optional. And it's a three-phase process. So WhereFault does all this work. Crashing host connects to the server, sends information a little bit about the file path of the binary, information about the user, the host name, not a lot of data, certainly no memory contents at this point. The crash server is then able to respond and say, I want lots of extra information, I'll talk about that. And then the crashing host says, great, here's all that stuff you requested, to within the best of its ability, within permissions, to service those requests. And it transmits it up as just a cab file with HTTP post. You can write a server that collects this in Python in 20 minutes, real easy. In XP Service Pack 3 and in Server 2003, it's substantially less useful. Error reporting happens over Samba, which is kind of cool. In the registry, you configure a UNC path or a local path if you so chose. And then it does a whole bunch of magic to pick a special directory hierarchy, and it looks for configuration information. It's a big pain in the ass. Unlike the more modern reporting in MS-SARE2, these hosts, the reporting is not interactive in any way. There is no here's a little bit of data, tell me what you want, okay, here it is. It checks for some text files. The only way to make it interactive is, in fact, just to set up a fake file system, if you're in the mood to do that, which is kind of cool. Or a fake Samba server, you can do that as well. All right, I'm going to leave behind those operating systems. I'm going to focus on what happens with the more modern operating systems. All right, so when it does the reporting over HTTP, if SSL is enabled, any certificate that Internet Explorer will trust will be trusted when reporting to the air server. So for instance, if you've got it configured to report to a server without a fully qualified domain name, such as crash server, anyone who has a cert for crash server from VeriSign is in like Flynn, so that's something to think about. The crash server, I'll talk a little bit about some of the things it can do. When a crash is reported, the crash server can do all kinds of cool stuff, such as enumerating the registry. It can run WQL queries, so that can control services. Program crashes, hey, turn off a bunch of services or query them or whatever. It can request arbitrary files from disk within the permissions of WhereFault. So if you have a piece of software running as local system that crashes, registry hives, right? I mean, the whole bit. Incidentally, as far as I know, Microsoft can request all these things. That's an interesting thing. Who knows if they're doing that? And then there's an enormous amount of undocumented functionality as well. And you can find this by running strings on wherefault.dll, or if you want to be serious about it, actually reversing it a bit. One of the things that we use is that you can request the crashing application's memory in totality. So if you want to download a 3 gig image from a crashing application, you can do that. I'm going to talk a lot about that feature. It's very handy. All right, so that was just some background about Windows error reporting. If you take nothing else out of this, I want you to think about the following thing. What could I do if I had a big network and I collected all the crash dumps? Because Microsoft has found out that's useful. You should find out how useful that is too. It's really easy. So here's what we did with it. We worked on a project for DARPA called Major Meyer, which is like a Marine joke, except we spelled it wrong. Major Meyer is a service that runs in your network. Hosts on the network are configured not to send crash dumps to Microsoft, but are instead configured to send them into the Major Meyer crash collector. When a mini dump is received, Major Meyer then attempts to answer the following question. Remember, this happens when a program is crashed. So we try to answer the question of whether or not the crash was caused by a routine malfunction or by a failed exploit. One of the interesting things about this is that this is not a preventative sensor. Networks are already full of preventative sensors at the boundary, and of course antivirus is also an effort to be preventative on the host itself. We are a post-mortem sensor. We attempt to identify that a crash is, well, by the time we're done with the work, probably already succeeded. So our hope is to take the period of time between ownage and detection and turn it into hours in an automated manner by looking at the crashes that were generated along the way. Great. So in order to add some substance to that and talk about what it means to look inside mini dumps for indications that an exploit has occurred, we need to talk a little bit about what causes exploits to fail in the modern age. The main things that we're going to focus on are these first two. Address space layout randomization. I'll say what it is just to solidify terms, but I presume we're all familiar with it. The whole notion here is that when an application or a DLL is loaded into memory, its position in memory is chosen randomly, subject to an awful lot of constraints, but essentially randomly. This works as a defense because an attacker who wants to inject code into your binary needs some frame of reference for their work. At the very least, they often need to know where their code has been loaded, and address space layout randomization is a thing which makes it harder to anticipate where your code has been placed. There are a number of workarounds. As an attacker, I will talk about several of them, which change the odds about this. It turns it from a bad guessing game into a reasonable guessing game. We'll talk about that a bit. The next, of course, is data execution prevention, DEP, aka the NX bit. This is an example of like what Intel giveth, no one useth. This is a feature that's been present since the GDT was introduced on IA32. But every operating system in use uses a GDT like a fool, and so this has only become popular in recent age with PAE in paged memory. The principle behind DEP is that certain pages of memory are marked as not executable, and at any time if the instruction pointer is aimed into one of those pages, a fault is triggered and execution is suspended by the operating system. Attackers usually put their code in places that are marked not executable, and so exploits often need some trickery to change those permissions. I'll talk about some of those workarounds as well and when they fail. And then, of course, I think that the oldest of these offenses in common use, the oldest offense is DEP, but in common use, stack canaries, which is just an attempt to leave behind values on the stack, of course, which, if modified, are detected at different points, leading to a crash. Did you have a question?
Redirecting EIP, right?
Yes.
Okay.
Yes, or RIP, or whatever, the instruction pointer on whatever architecture. Yes. Great. Here's an attack that doesn't work anymore. So like at universities across the planet, here's how you be a hacker class, like they run on goofy modified Linux kernels so this attack will work, or with goofy GCC so this attack will work. Is vulnerable, has a buffer, it scanfs in, stack grows down, execution grows up, attacker wants to send some random bytes, pointer to ESP, which is where the shellcode's going to be, and then there's shellcode, and the idea is that you return into jump ESP, which then jumps in your shellcode. This is awesome. There's a lot of reasons why this won't work anymore. The big one is that ASLR prevents an attacker from knowing where to find jump ESP. This is a common trick, but I'll talk about it anyway. The whole idea with this kind of thing is that jump ESP encodes as 2 bytes on IA32. Those 2 bytes are likely somewhere in memory, even if no compiler specifically emitted the jump ESP instruction. So there you go. As an attacker, the main thing that makes this difficult, never mind stack canaries and execution prevention, is knowing where to find a jump ESP. In the presence of ASLR, I don't know where that is. Even if an attacker can find it, DEP prevents the shellcode from executing because it is on the stack, and stacks are not executable unless shenanigans is already taking place. And regardless, stack canaries prevents it from going. So there's a lot of reasons why that vulnerable code doesn't actually lead to a working exploit. Working around this stuff. So the whole idea behind ASLR is that it is a numbers game. When the address space is random and the attacker has to guess the location of their shellcode, they can just say, well, gee, I ran it this one time and it was at this address. I'm always going to guess this address. And the probability of that succeeding is extremely low because there's 2 bytes of entropy or more present in the addresses when the application is loaded. So a common workaround is to just put several copies of the shellcode or whatever the payload happens to be in memory. The most common form of this attack is the heap spray, which was discussed several years ago. I don't remember the citation. Someone remembers the citation. Yell it out. That's really sad. All right. Great. The attack is really straightforward, though, in the sense that you just put more copies of the payload in memory if the bug makes that possible. JavaScript engines are a great example of when you can do that. And the more copies of the payload are in memory, the more likely that you will guess a correct address for one of them. So in the limit, you can fill memory with all your stuff and have total success, but of course in the limit you've overwritten the entire address space, so execution probably isn't working anymore. So in practice, you look for a compromise and maybe spray out the heap and fill in like a gig of copies of your stuff in the heap, or maybe 2 gigs or however much. So that's a common thing, just playing with the numbers game. Another common bypass for ASLR is to just overwrite the least significant bytes of a pointer in memory, which already points approximately into the right location. This works on Windows, at least because in Windows, ASLR only affects the most significant bytes. Those are the random ones that you can't guess. But if you know that there's this pointer that's already pointing, say, into the heap, near some place where your code's going to be, you don't need to know the most significant bytes. You just have to be able to change the least significant bytes and move that pointer over by a couple kilobytes, and then you're in business. So that's a very common thing. That's the partial pointer overwrite. Really, really slick, very reliable. In terms of depth bypasses, there's like an awful lot of different choices here. Probably the most straightforward one to execute in lab is to just use return-oriented programming to change permissions of memory. So, for instance, on Windows, the virtual protect routine is a routine that you can call at any time in your program to make a page executable. My understanding, and I'd love for someone to tell me I'm wrong about this, my understanding is that as an application developer, there's no call I can make to disable subsequent calls to this. Just tight. Because the number of programs which have a legitimate reason to call this, to make something executable, is like not most programs. Most programs people attack, perhaps, but not most programs. So as an attacker, without executing your own code, you can often invoke a false code call in virtual protect using return-oriented programming, basically just setting up false call frames, then returning through into that, make your pages executable. So in practice, a good attack against a modern piece of software on Windows will involve a few of these tricks. You need to be able to work around address space layout randomization, both so you can call virtual protect and that you know which pages to modify. You need to be able to work around depth using this technique or perhaps using other techniques which are more indigenous to the application. For instance, if the application does its own code generation, something of that sort. Lots of different things. This is not a lecture on exploitation, so you'll have to consider several other options as well. I do need to talk about return-oriented programming, though, more, just because it is an important thing to be able to detect in memory if you're looking at crash dumps. So return-oriented programming can be used as an alternative to shellcode. It can be used in conjunction with it. The basic premise is brilliant, subtle, wonderful. It should have been obvious to everyone. It seemed to have not been. The basic idea is that the CPU will... There's really two things going on here. One is that the CPU will attempt to decode whatever IP is pointing to. On x86, if you're not an assembly programmer, I'll spoil the mystery for you. Instructions are not aligned in any meaningful way. Some instructions are 1 byte long, some are 5 bytes, some are more than that. Whatever length is clever. Most sequences decode as something. And most of those things that decode as are actually innocuous and don't really affect the state in a meaningful way, depending on, relative to what you're trying to do as an attacker. So for example, FFE4 decodes as jump ESP. Anywhere in memory that there's an FFE4, if you point the instruction pointer at that, it will jump to the stack pointer, even though jump ESP is an instruction that no compiler emits in usual operation. The whole idea for return-oriented programming is to take that as a starting point and then recognize that return is a 1-byte instruction, which means it comes up all the time, and to sequence calls of weird decode chains like that together by creating false frames on a stack that the software will then return through in order to chain these together. There's an enormous amount of information online about this technique, and if you've never worked with it, it's a real joy. Great. Why exploits fail. This is a topic. If you're someone, by the way, who's like thinking I should talk at a con and I don't know what to talk about, please talk about this some more. It'd be really great to see systematic studies of this problem. Why exploits fail, I mean. So the two main things that we've been looking at for our project, just to kind of get the ball rolling in terms of this sensor, are the failure to gain code execution itself, such as the heap spray failed, or the target program is in the wrong state, or it's the wrong version altogether. Basic things like that, or the shellcode itself fails. Target host policy got in the way. Program is again in the wrong state. Some decoders are kind of cantankerous, especially in the presence of certain transforms on the network. So these are the kind of things that we've been looking for as evidenced within memory dumps. All right. So what we do in Major Meyer is we look for signs that the stack has been manipulated. And when we say the stack, we mean either the stack given to us by the application's loader, or the stack given to the application by means of a stack pivot during some kind of a ROP attack. So that's one of the things that we look at. The second thing that we look at is signs that shellcode resides somewhere in memory. And I'll spoil something for you right there. We're not talking about regular expressions when we say we're looking for shellcode. I'll talk about that for sure. All right. Are there any questions so far? Cool. Sorry, sometimes I go back into teacher mode and ask that. There's never questions then either. All right. The stack. So here's an observation. This does not have to be true. There's nothing in the Intel documentation or the AMD documentation which mandates this. But as it happens, most functions in most programs manipulate the stack in very, very simple ways. Anyone who's done any kind of reversing knows this already. They allocate space on the stack. They reference locals. They use the stack to pass parameters, certainly on 32-bit, to a lesser extent on 64-bit. And they use the stack to save state between calls. So based on that, there's this idea when you're trying to do static analysis with a crash dump in hand that you should be able to model the behavior that each function has on the stack, basically eliminating lots of instructions in the disassembly for that function which don't modify the stack. And based on that, each function has a bit of a signature that it leaves behind when it's invoked. Residue that's left on the stack even after it's returned, because of course returning doesn't clear memory, that provides a hint that at this time, at this place, this function was invoked. For some functions, the signature is not very unique at all. Lots of functions will look the same. For very interesting functions, functions with bugs very often, these signatures can actually be quite unique. So, based on that, you should be able to take a look at even a corrupted stack and use these signatures to form a hypothesis about execution. Debuggers do this to some extent, but because debuggers don't want to provide misleading information, they tend to abort early. But if you're looking for certain kinds of pathologies caused by unreliable exploits, you can use these signatures to form a theory about which function was actually attacked and how code execution got there. And once you form that theory, if you find additional residue that looks like calls, but which doesn't line up to any of the signatures you've identified in the source code, then you can be reasonably certain that those are in place either because someone has fabricated them for return-oriented programming or because shellcode is already executing and using the stack. So I'm going to talk about two different models for how to do this. And this is really the heart and the theory of the stack analysis. The simple model, quite straightforward. You chunk up the stack memory into D-word or quad words, depending on if you're a 32 or 64-bit application. You then look for values in that region which might be pointers into executable regions of memory. And you can do that because the mini-dump will tell you exactly what the permissions are on every page for the application, including pages that the mini-dump hasn't supplied. Although, again, if you use this undocumented feature, you can get all the memory anyway. Now, this is a heuristic. ASCII text can generate D-word and quad word values that look like this. But, more or less, though, when you encounter these values, they should point to function preludes, which, either you identify at time by looking for instruction. We know what function preludes look like, or you identify them through a prior disassembly. They should be pointing to return points, instructions which follow a call. Those are slightly harder because you can't disassemble in reverse, but you can still do this. They should point to return points to other instructions, which is a little bit trickier. This comes up when you're in the middle of, when like an interrupt is fired, something of that sort. Then an address will be pushed onto the stack, which points to code, but wasn't caused by a call, and it's not a function pointer, but that's okay. The big challenge with this is that you can't disassemble in reverse. And that's, again, simply because instructions are not of fixed size. So what you do is you disassemble the binary in advance using all the usual heuristics. You follow call points, you follow pushes into executable regions, you go through data sections looking for V tables, things of that sort. And then you build this gigantic model so that you know this instruction is preceded by that instruction at this location, and then you can check it. So a little bit of prior disassembly makes this very straightforward. And again, the main focus here is that you want to be able to answer the question of whether or not a given address points to an instruction that was generated by the compiler versus, say, some sequence of bytes which just happened to be in memory. This model executes like that, even for enormous crash dumps, because its complexity is bound by the disassembly complexity of the program you're looking at, which is something you can cache, and it's bound by the size of the stack, which is not often that big. So just linear time through the stack, real easy. The main challenge is, of course, that it's hard to account for pointers pushed by interrupts. If the program is crashed, I guarantee that will be present because of SEH handling. But if you allow for that and you know what the locations of SEH handlers are, you're good. It cannot recognize ROP into a function's entry point. So if a person deliberately pushes pointers onto the stack that are function entries, that will seem legit to you, even though it is not. And this has a hard time following stack pivots, sort of depending on how you handle this. That's an implementation detail. A less simple model of what the stack might look like. So if you want better resolution and better reliability out of this kind of a process, you can go ahead and start with the same disassembly and just build a large call graph in simulation, in the same way that IDA does, for instance, which will give you some additional information about not just what the signatures of functions should be, but also what sequences you should actually see present in execution. You can augment that understanding as well with a little bit of simulated execution, basically ignoring the state of registers and just following calls and stuff of that sort as much as is necessary if you want to get real fancy. If you want to push it even further, you can set up a constraint solving system that does the same. All those are wonderful things for a grad student to do sometime. Which is not me anymore, so I'm not going to do that. So you go ahead and decompose each function into these graphs. You have edges for control paths, and then you're in business. When you analyze the stack, you do the same thing as before, but now not only do you have a theory about, this is a pointer to this function, that's a pointer to that function, but you can also say, golly, I can't explain where this address came from. Oh, that's okay. That's in the middle of some memory allocated by that function. I don't have to sweat it. Or, gee, that is a pointer to virtual protect, which is a real function, except that's located where this guy thinks he's going to return to, which shouldn't happen. And so when you have this greater knowledge about what chains actually make sense in the application, you can really drive up the reliability of this model. So I went ahead and I wrote a simulator for that. And of course, I had to get a sense of what possible paths my disassembler thought might occur. And so I did what any good computer scientist would do, and I used GraphViz to produce some images. This is a snapshot of an image that reliably crashes Internet Explorer. So, if you're looking for something interesting in IE, take a look at SVGs. This image here came from a disassembly of a program that has 20 lines of C code coupled with the Microsoft C runtime. The program is very small on disk. The memory size of all the semantics that I built up for it expanded beyond 10 gigs in execution. I'll talk a lot more about what information is in there. So if you're going to go ahead and build a graph that represents all the possible call chains that might occur, the main thing that you're going to want to do is form some hypothesis about which call chain actually led to your crash. To do that, you have to go through a graph traversal problem. The main issue here is that there are reentrant functions with variable recursion. It is an interesting, tractable problem to go ahead and detect that you're in a loop in that context, because if you are only simulating the state of a single stack, you are provably not Turing complete, and the halting problem does not apply. So what we did in order to handle that is we proceeded by way of a light emulation, simulating only stack-related routines, maintaining state for no other pointers or no other registers besides IP and SP, following through to try and build a hypothesis of where the program was when it crashed, so that from there we could form a theory about what state the program was likely in if shellcode was then to follow in execution. The big challenge with this is that the size of this graph is quite large. You cannot enumerate it and then proceed from there. Because of variable recursion, you have to generate it as you proceed. There's a fascinating problem here for anyone who's interested in concurrent execution of graph algorithms, that the basic execution step is inexpensive, which means parallel execution is hard because of locking primitives just then serializing a bunch of small steps. So that's a fascinating thing. There's a lot of room for improvement here. Anyone who is interested in collaborating on this problem should talk to me if you have experience in parallel graph algorithms. Okay, I've talked a lot about the stack, and not a lot of guys are excited by the stack, so we're going to move on from that. Let's talk about shellcode, which is actually calculator code these days, but cool, shellcode. So if you want to find shellcode in memory, the main challenge that you have is that regular expressions can detect common payloads, but they're ad hoc. I think anyone who's looked at Snort knows that the basic approach to signature-based detection of shellcode work grand for people who download shellcode from popular websites, and doesn't work at all from some guy who's got a real thing going on and writes his own, or who just uses a non-standard packer. So regular expressions, not great at detecting shellcode against serious threats. They only really catch boring stuff. On the other hand, when you look at shellcode from the perspective of execution, it has a lot of conspicuous behavior. It is code which is not loaded by the loader. That's weird. It doesn't actually know the locations of system calls. On Windows, you need to find those out. And very rarely does legitimate code touch the PEB structure in Windows, but shellcode does it all the time. And so Mikhail is going to talk about the following principle, which is really important for crash dump analysis for execution, or for shellcode, which is that nothing hides from execution.
So basically our main goals for the actual emulator itself were to be able to reconstruct the full address space as present in the mini dump, and then iteratively step through that and execute it from every possible location. And on top of that, use heuristics to actually go and try to find address-independent shellcode. So the benefits of emulation are quite simple. Basically, nothing can hide from emulation, from a good emulator at that. It can defeat most encoders and packers, since you are actually executing the code in an actual environment. And as an added bonus, you actually get to find out what the shellcode was trying to do and how it was trying to accomplish those things. Some of the disadvantages with our approach, at least, it's pretty slow. Right now, we're getting 1 to 2 million instructions per second, with bursts up to 5 for certain instruction sequences. The other problem is, again, variable width instructions. We actually have to start emulation from every single possible byte that we target for emulation, and we have to do direct instruction splitting. That is compounded with the problem of extremely large dumps. Say Photoshop crashes. Now, great, you have a 2 gigabyte dump. That is quite slow. Also, we had to, another problem is that various passes would go ahead and corrupt the running memory image itself. So we had to actually be able to reset it back to a state back to the state present in the mini dump for every single pass that we did. So some of our technical goals were basically to support both x86 and x64. We basically had the concept of doing good enough emulation, where we didn't want to recreate all the instructions, but all the ones that we felt were going to be appropriate for detecting simple payloads such as shellcode. So we didn't go ahead and implement all of the x87 floating point instructions. We just went ahead and implemented, FST, NV, and FXSave. which I will talk about more later. So also, this entire project was myself and him. We would not have been able to actually go ahead and implement every single instruction in the amount of time that we had to do this ourselves. And we couldn't use Box or QAMU because of various technical limitations within them. So our approach primarily focused on offloading as many instructions as possible to the native host CPU. And the way we did that is we basically generated directly from the Intel ISA. We were able to create wrappers for every single instruction and every single permutation of arguments there and automatically generate, I believe it's like a 5 megabyte assembly file, which allows us to pass in various arguments to it and have it execute. This allowed us to basically capture all the instruction nuances without actually having to rewrite every single instruction. Basically, the way those individual stubs work is by loading up instruction-specific context, such as if you're doing a compare, we would load in the R flags register, perform the instruction, and then save off that state and return our emulator's internal state. For example, here's a simplified version of what we do. So a normal instruction such as move EAX5 as present in the dump would evaluate to loading in the immediate value of 5 into EAX and then move it into a register pointer that we have in our context. So since these were precompiled stubs that we added to the emulator in that 5 megabyte assembly file, we had issues with dealing with immediate values that are encoded into many instructions, such as referencing ST3 and ST5. We were not able to actually accommodate for that, and so we had to actually develop algorithms to perform a best fit operation between what combination of arguments we could use to actually do the same thing as the original instruction itself. In the future, we would like to probably use JIT assembly and then cache off frequently used instructions. Also, another issue was our emulator was 64-bit, and context switches between 64 and 32-bit are pretty expensive, so we had to go ahead and re-implement most of the 32-bit instructions by hand, which was annoying. As far as being able to reset state quickly between individual emulation passes, what we did was we created a taint propagation model where an instruction that actually has the potential to modify a value inside of a pointer that is passed in would mark the entire memory page as tainted and would be restored upon reset. That way we didn't have to actually reinitialize the entire memory image, but just only portions at a time. One problem is that our current system does not differentiate between direct reads and writes, so typically you get resets pretty frequently, but it's only one page at a time. So ideally, in the perfect world, we would like to start emulation at every single address that is present in memory at the time of the crash. Unfortunately, this is completely and utterly unrealistic due to dump size. Our current system running on a single core, a 2 gigabyte dump with an average of 500 microseconds per emulation pass would still take around 10 days to do. So what we primarily did was narrow down the focus to pages on memory pages that are used for the heap, the stack, and anything that might have been used for file backed I/O. This greatly reduced the actual starting addresses that we should actually perform emulation on. Also, we prioritized addresses that come in from the stack analyzer that it deems to be important enough to actually investigate further. We perform kind of a simplistic deduplication of execution, where we keep track of state between individual instructions, such that if they do not modify memory or stack, we can flag them as already been simulated, and that lets us drastically reduce simulation, especially on the naturally occurring loops that you find in ASCII strings, such as an example on the slides. The first pass would execute push EX, that would modify the stack. It would go through this entire thing, and then the next time it would start going through the NOPs. It would start the NOPs. Notice that the 5,000 NOPs have done absolutely nothing, mark all those instructions as already simulated, and then that way this lets us actually significantly reduce the occurrences of these loops as we hit them. And also, as we use progressive heuristics, we can set a relatively low instruction limit for the maximum number of instructions we're going to execute per pass. That way, we only hit very large loops only once and not for a very long period of time. So once we hit one of our heuristics, then we multiply or increase the maximum instruction count by about an order of magnitude. As far as self-locating, so some of the heuristics that we actually collect and try to analyze. So for self-locating shellcode, the x87 extension allows for, since it was designed to be a coprocessor, it keeps a lot of internal state and provides several instructions for saving and loading its internal environment. So the instructions fst, env, and fxsave have parameters in there, or pointer, basically the save-off structures which contain the instruction pointer of the last FPU instruction that was executed in them, and it's used commonly in shellcode to actually figure out where the code is actually located. Typically, it's the FLD pi. Also, another common semantic is using call and pop. Basically, you call and then you call immediately after the call instruction and then pop off the value, since all that call did at that point was save off the return address, which is going to be the location of the pop itself. We detect this by, well, going back one bit, we detect the FPU Yeti IPs by just basically looking for the instructions. Very, very rarely are those actually called in a normal program. For the call pop, we build our own individual stack of what addresses the return address is stored. And for any given call frame, if that address gets dereferenced, we tick that checkbox. Find eggs we don't really care about at all, just because the emulator eventually will find where the find egg is actually trying to find itself. This is not very useful for x64, since x64 uses actual RIP relative addressing, so there's no need for shellcode to self-locate usually. As far as syscall usage, so again, due to ASLR and inconsistencies in Windows syscall numbers, shellcode is often forced to actually go and find the image bases for all the loaded modules. So say if it wanted to access Virtual Protect, it would actually have to go figure out where that is. So we detect this by looking for accesses to first the thread environment block, then the process environment block, and then finally the PEB LDR data, which is where Windows keeps all the information about the loaded modules themselves. At that point, shellcode typically goes ahead and enumerates the exports there and figures out where the functions are that it needs to call. So we basically, again, we just literally detect the touches to the resources. And we also monitor when the instruction pointer actually ends up going to one of those protected functions, as well as when one of those restricted functions, such as virtual protect or get proc address or load library or any of the WinSock calls. And on top of that, in the cases where, say, a ROT payload would end up going to the middle of the function because it just wants to skip some of the initialization, which it probably did itself, then we also perform the exact same export resolution upon the actual syscall instruction or whatever that boundary is. This basically gives us all the data we need to be able to give a general sense of intent and malice. And if all these things happen in an address-independent way, then we know this was probably malicious. So there are some of the technical details about the emulator, and I'm going to hand it back to Volker.
Sweet. So just to wrap it up a bit, and tie it back up to our disclaimer slide as well, there's an enormous amount of future work done in this direction. Aside from our project, and in the course of our doing our research ramping up into it, I'm not aware of other automated systems which look for signs of attack by collecting crash dumps. But this is an area that's very fruitful for additional work. There's a lot of even low-hanging fruit that we hadn't even, we considered but didn't really explore implementing in any serious way. Heap sprays are so common, so easy to pull off, so reliable, and they look very conspicuous. This is a thing that an n-grams approach might just outright solve and detect every time. Someone really should be looking into that. Another thing, especially if we're going to be analyzing actual stack frames, as we're already doing, we can add some semantics to that. There's an awful lot of important functions whose semantics are just well known, either because they're libc or because they're Win32. You can anticipate them. They're not indigenous to applications themselves. If you find residue from these functions, you can use that to start looking for important things. I gave here a trivial, perhaps not even very practical example of looking for information disclosure being triggered by looking for calls to sprintf. More sophisticated versions of that are more real world probably do exist and just need to be found. Of course, performance improvements. In the enterprise, your worst case scenario is that you have a fancy sensor that works great for post-mortem analysis. The attacker knows this, and so they just DOS by intentionally triggering a ton of crashes as cover fire. Performance improvements are really the first, most serious kind of defense against that type of thing. Built-in awareness for compiling techniques of different languages. There's probably an enormous amount of potential here to leverage the work that's done already in static binary analysis to recover some semantics from the higher level languages based on how code is being built. Anyone who's reversed Objective-C code, for instance, knows that it is substantially, obviously, in important ways different than reversing C code. We aren't really taking that into account so much, and there's probably an awful lot to be had from there. Someone here who's an expert in that build model probably could accomplish quite a bit. And then this last one is going to remain just the bane of our industry for all time, dealing with JIT code. Yeah, there's just so much around that. So that's it for our story. I'm Tim Carstens. That's Mikhail Davidov. We want to give our thanks to DARPA, to Brother Mudge, to our intern this summer, Zach, who worked with us on writing the task scheduler. And open it up for questions. Thank you. So because this is DARPA work, the source code is not exactly ours to release. So the release process, and this is relevant if you're interested in Cyber Fast Track as well, is that you say that you want to release something and then DARPA spins their wheels for some period. For our slides, for instance, it was about 2 weeks, basically to decide if there's an impact here to the government's research interests. So we don't have clearance yet to do any kind of code release. However, if you would like our source code, and I promise it is horrendous. For instance, some of it is written in Haskell. If you are interested in our code, you're welcome. If you are interested in our code, probably the most realistic way to get it is to send a FOIA request to Mudge, which will be funny. So, you should do that.
Right now at DARPA, is it their goal just to keep it at the DoD and the government level and eventually to the civilian world? Or?
So I've done several DARPA projects, both with Leviathan and with other contractors in the past. To be perfectly clear, and in contrast to what Wired reported about the Cinder program, DARPA work is predominantly focused on building technologies which are useful to the national security of the United States and its allies. This would include work which is valuable to the commercial sector, but which is of a defensive nature. I don't hold a security clearance. Mikhail doesn't. Nothing about our work is classified in this, which automatically means that there's no offensive capability to it. Mudge is very interested in providing incentives for small businesses, especially, but also medium and larger performers, to design original high-risk research that can turn into viable commercial products. So, if you've ever wanted to do R&D and don't want to, give that away to an investor, Mudge is your man. I don't know if that answered your question, but it's all true. Yeah, it answers a question.
Have you investigated caching, basically multiple runs of caching to perform? I mean, it fails along its logic hard, so you have to test a lot.
Right. Absolutely. So along the caching lines, one of the convenient things, especially when you have a full image dump, is that all of the PE headers from the executable itself and its modules will be present in memory, And unless someone has invoked virtual protect and marked them writable and then trounced them, you can trust it. So, for instance, hey, ASLR is turned on for this crashing program, but I know the base address that's expected, I know the base address that was loaded, and yes, that makes caching possible. For the shellcode analysis, we explicitly avoid executing shellcode detection on code supplied by the binaries themselves, under the assumption, perhaps false, but under the assumption that that hasn't been modified at runtime, since those pages are usually not writable. So in terms of caching for shellcode emulation, you're looking at heap stuff. Caching is not useful in that context. For the stack modeling, which is very expensive but very cacheable, yes, absolutely. Yes?
How do you feel about the new security protections that we offer in Windows 8, specifically to make it harder to write exploits for?
Good. I haven't looked at them in enough detail yet to really feel comfortable going on record about that.
The only one that I've looked at so far has been the ROP mitigation one for the virtual memory functions, and it's pretty easily bypassed, but you just need to rewrite your ROP payloads.
Right. I think that anytime there's a question about a forthcoming version of Windows and a new defense, the answer is always time will tell.
Does the default Windows crash reporting use SSL?
So reporting to Microsoft does use SSL, I believe, but I'm not really in a position to speak in totality on that because I haven't reverse engineered stuff I don't own officially. In terms of running your own crash server, it's trivial to enable SSL. Like I said, any certificate that IE trusts will be trusted by Windows Error Reporting for the host that you're connecting to. If you're in a corporate environment, you might strongly consider deploying your own certs and only trusting those, perhaps, in as much as that's practical. Certainly for infrastructure, you should do that. We're going to wrap up at this time. If you have more questions, Mikhail and I would be really excited to talk to you in the hall. Thank you.
Great.
Cheers, man.